Hello students, my name is Sumit Sagar Hota. I am a PMRA PhD student at IIT Palakkad. This is the week 6 of the live discussion section. In these sections, we will cover lecture 26 to lecture 30 by Professor Ashok Desar, IIT Kanpur, of the subject Introduction to Airbreathing and Propulsion by NPTEL. Okay. This is the week 6 of the live discussion section. In this section, we will solve some of the MCQs and we will solve some of the numerical problems. Okay, let's start the first question. The axial flow of turbojet have about dash less specific fuel consumption. Okay, so the answer of this question is A, which is 6 to 8%. Okay. Okay. Okay, the next one is basic cycle of turbojet engine is what? It is both what? Joule cycle and Brayton cycle. Next is turbojet engine is a dash, say what? Continuous. Okay, it's having a continuous flow regime or it's a continuous flow engine. Okay. Next is turbojet engine is eminently suited for propelling aircraft at speeds of what? it's actually very high speed. It will be above 800 km per hour. The turbofan engine was originally conceived as a method of improving the dash of the jet engine by reducing the mean jet velocity. Okay. So the turbofan engine was originally conceived as a method of improving the propulsion efficiency of the jet engine by reducing the mean jet velocity. Okay, we didn't consider here the thermal and overall. We'll consider here for the any kind of turbojet engines or any turbofan engines, we always first consider the propulsion efficiency. Okay. The turbofan engine are usually described in terms of obviously a bypass ratio. Okay, don't confuse the bypass ratio and bypass factor. Okay. So if you actually want to know what you called bypass factor always use in the what in place in the study of RAC, refrigeration and air conditioning. In thermodynamics we studied this bypass factor. Okay, and just a brief overview of bypass factor I will give. Okay. If if there is a in a flow, if there is a constant area duct and there is a some heater or cooler, either options will be there, which temperatures are given. Okay, So if a flow will pass through a heater or a cooler, so the T naught whatever will be there will going to increase or it's going to decrease. Okay, so that's what the, and then we have to actually calculate the what do you call bypass factor. First of all, I will draw some of the graphs for the better understanding. If there is a if there is a heating, let the temperature is Ts, which remains constant throughout the time, and if the initial temperature is somewhat Ti, it will gradually increases when there is a flow occurs through the duct. It depends on the time or it depends on the position of the duct, from Ti position to the T naught position. Let Ti equal to T ambient. Okay, so this is one case. This is your what, heating. So in the same way, if there is a cooling, the Ti will be higher and Ts will be less, and the temperature will going to what, decrease. So what is the bypass factor? The bypass factor equal to mod of Ts minus T naught divided by mod of Ts minus Ti. Why mod? Because depending on the positive or negative sign, it can be changed. Okay. Okay. So this is the bypass factor, and for any kind of turbofan engine or turbojet, whatever, so accordingly the bypass ratio are there. Okay, so don't confuse with that two things. Okay, now let's consider okay, from this we actually can write down the ratio. What is the bypass factor, the real definition of bypass factor, then we'll go to the what, bypass ratio. Okay, so the definition of bypass factor is temperature drop or increase not achieved divided by temperature drop or increase that could be achieved ideally. Okay, now let's come to the bypass ratio. Now the bypass ratio is the flow through the flow through the bypass duct cold stream divided by flow at entry to the high pressure compressor which is a what hot stream. Okay, so more specifically we can write down then in some of the questions actually they will give you the what you call bypass ratio, then they want this m dot c and m dot h. M dot c is your what, this is your m dot c, this is your m dot h. Okay, so bypass ratio is equal to m dot c by m dot h. Okay, so what is m dot c? M dot c is equal to m dot total into bypass ratio divided by bypass ratio plus 1. M dot h is equal to m dot total divided by bypass ratio plus 1, where m dot total is equal to m dot h plus m dot c. Okay, so these are the maybe this type of questions, 1 mark MCQ they can ask. Okay, so obviously whatever now I told, the same definition they are asking. The bypass ratio defined as the ratio of the flow through a bypass duct to the flow entry to the what, hot stream. Okay, because cold by hot. Okay, so it's answer A. The term turbofan was originally used for engines of high what? We are telling all these things, bypass ratio. This obviously used in what, turbofan, so this is the answer. Okay, originally it was bypass ratio are used because turbofan is having what, high bypass ratio. High bypass ratio means your flow through the bypass duct, that is the cold stream, that is m dot will be higher than the whatever it's coming to the high pressure compressor. Okay, that is the hot stream. Okay, okay, so now we solve one problem. It's a little, actually very lengthy problem. Okay. Okay, you slowly go through this problem. This problem is really important. Okay, just a second. Let's start the problem. The question is determination of the specific thrust and specific fuel consumption for a simple turbojet engine having the following component performance at the design point at which the cruise speed and the altitude are m 0.8 and 10,000 meter. The compressor pressure ratio is 8. Turbine inlet temperature is 1200 Kelvin. The isentropic efficiency of the compressor is 0.87. The isentropic efficiency of the turbine 0.9. For the intake, the isentropic efficiency is 0.93. For the propelling nozzle, it is 0.95. Then the mechanical transmission efficiency or the mechanical efficiency is 0.99. Combustion efficiency is 0.98. Combustion pressure loss is 4%. Compressor delivery pressure. Okay. This question is very simple to see, but it's not that much simple to solve. Okay, so we just slowly go through this problem. So okay, so first of all we'll write down the solution. Directly we'll go to the solution. So first at 10,000 meter, what are the things given? Okay, if you see at 10,000 meter, nothing is given in the question. Okay, so those some if they are giving this question, they have to give the one data table with respect to the height, what are the pressure, temperature, and the what is the actual velocity at those positions. Okay, so those things they have to supply, okay, in this type of problem. Okay, so most probably this kind of problems will come in UPSC examinations or IES. Okay, so yeah. So PA will be your 0.265 bar, and TA they have to give us 223.3 Kelvin, and that position the sonic velocity is 299.5 meter per second. These values are what given. Okay, so if these values are given, then we have to find out the stagnation condition after the intake. Whatever the term I am telling, all these terms itself is a 1 mark question. Okay, like they'll ask you the question, what is the, okay, these are the things given, then at the 10,000 meter your pressure is this, temperature this, and your velocity is this, and then find out the stagnation condition after the intake, or directly they will ask you what is the stagnation condition. Okay, so yeah, that means you have to actually find out the what temperature, different temperature in Kelvin, they will supply you the values. Okay, so those types of question can be very easily asked. Okay, so for that you need to know the what formula of the stagnation condition. This is actually the last question of this section, so we just solve this question, then the sections will be over, but it will really take time. Okay, maybe some 30-40 minutes maybe. Okay, so stagnation condition after the intake. So what is the formula? This CA square. Okay, it's not like that. CA okay, so what is a Mach number? Mach number is equal to your actual velocity divided by sonic velocity. Okay, so now in this question, okay, you can add directly it will be difficult for you to understand. I'll write down like this CA. Okay, CA means you may be confused with ambient also, right? So I'll remove this completely CA term so that it will be easy to understand. Okay, so this is your actual velocity divided by sonic velocity. So to find out the actual velocity, you have to multiply with the what, m into c, that is your actual velocity, right? So okay, m into c whole square divided by 2 cp. Okay, So you know what is the Mach number in this question? The Mach number given is what? 0.8. Okay, so what we will do, we just multiply 0.8 into 299.5 square divided by 2 into CP. Is CP given? So basically CP here in the question not given. CP is not given. So take the general value, whatever value is there, that is your CP is more or less, we assume it as constant, and the value is 1.005, but actually it's not constant, it can vary with the altitude, but we are assuming it as constant for the simplicity of the problem. Okay, since it is not mentioned that it will vary in the problem, it's not written, so that means we can assume it as a what? Constant quantity. 1.005, the unit will be kilojoule per kg Kelvin, but here it the numerator in SI unit, so we need to actually multiply it 1000, and the answer will be 28.6 Kelvin. Okay. Okay. So then what we will do, we will find out the temperature. We will have to find out the temperatures. Okay. So for that we need to plot the TS diagram. Okay. Okay. This is your T, this is your S, TS diagram. If you can see, this is your 1 to 2, this is your ambient pressure, so this will be your 1, this will be your 2, okay. So next, this is your whatever the loss it's there, okay, delta PB, okay. Next here 1 cycle, okay. Okay, this is your 4th, this is your 5, okay. This is your actual cycle, okay. This will give your 4 dash, okay. So what is P5? P5 is equal to PA, or we can tell PC, okay. Okay, so now so T1 we just find out, T1 is equal to TA plus CA square divided by 2CP, okay. Okay, so it's actually not CA square, we actually renamed it MC square. Okay, so it will be your what, MC square. Okay, MC square by 2CP. Okay, so what is the TA value? We already have the TA value. If you can see here, TA value is 223.3 Kelvin, and MC square by 2CP will get 28.6 Kelvin. So what we will do, we just substitute all these values and find out T1. Okay, it is 223.3 plus 28.6. T1 is equal to 251.9 Kelvin. Okay, so now we'll take the ratio P1 by PA. Okay, that is P1 by PA. P1 by PA, 1 plus eta I CA square divided by 2CP into TA to the power gamma by gamma minus 1. Okay, in place of CA you can put MC square. Okay, so what I will do, we'll just substitute the values. Okay, what is eta I? Eta I is your what? Eta I, you see, intake. Okay, the value is 0.93. Okay, the isentropic efficiency at the intake is what? 0.93. Okay, so we have to just what? To just substitute in the ratio in P1 by PA. Okay, now We'll just substitute. Place P1 by PA is equal to 1 plus 0.93 into 28.6 divided by what is the temperature of Cp into TA? 2 into 1.005 into 1000 into 223.3. Okay, to the power what? Gamma by gamma minus 1. If you put 1.4 gamma, then what will be the ratio? It's 3.5. Okay, here gamma is, we are taking what? 1.4 we are taking. Okay, assuming is at what? Because in the ambient condition, because A is your ambient condition, and in the ambient condition we are having only air. Okay, there is no change in pressure of the air, so that's the reason why we are considering the air gamma as what? Cp by Cv ratio as what? 1.4, and that's the only reason why we taken 1.005 as the Cp value at the ambient condition. Okay, so now just solve it and get the ratio of P1 by PA. If you solve, you will get P1 by PA as 1.482. Now you know what is PA. That is, what is PA? PA already found from the height of 10,000 meter. You get the PA ambient condition as 0.265 bar. Okay, then what will be your P1? P1 is equal to 1.482 in just 0.265. okay, 1.482 into 0.265. okay, okay. So P1 is your 0.393 bar. Okay, okay. So now we have P1. So now if we have P1, then we can calculate what? P2, because there is a term called what? Compression ratio. Compression pressure compressor sorry compressor not compression, it's a pressure ratio. Compressor pressure ratio. Okay, compressor pressure ratio equal to 8 given. Okay, and where is the location of compressor? It is in the position 1 to 2. Okay, that means P2 by P1 is equal to 8 already given, and we have P1. So P2 is equal to pressure ratio into P1 is equal to 8 into 0.393. So P2 is equal to 3.144 bar. Okay. 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 Now next there will be a term called what? Isentropic efficiency of a compressor. So you see, isentropic efficiency of a compressor 0.87 given. Okay, so now we target that, because there we can find out the values of T2, because we have P2, we have P1, we have T1. Now isentropic efficiency of a compressor relates the T2 by T1 ratio. Okay, so we can easily calculate this. Okay, now there is two cases. Okay, so isentropic efficiency is equal to T2 isentropic minus T1 isentropic. T1 actually actual, because T1 there is no difference between T1 and T2. Okay, divided by T2 actual minus T1. Okay, so what is the isentropic efficiency? 0.87 is equal to T2 isentropic, we don't know, but you know what, T2s is equal to T2s by T1 is equal to what, P2s by P1 to the power gamma minus 1 by gamma. Okay, okay, so P2s by P1, or which is the pressure ratio, what is the value, that 8. Okay, we already know the pressure ratio is what, 8, and gamma minus 1 by gamma 1.1 by 3.5 we can write down. Okay, so this is your 8 to the power 1 by 3.5. okay, but now we have to multiply actually the what, T1. Okay, then only we can find out what, T2s. Okay, so now we can take common of T1. Okay, and you can put substitute there in this equation. We'll lie down the next page. So is equal to 8 to the power 1 by 3.5 into T1. What is the T1? Okay, let's just write down first T1 minus 1. Why? Because here also T1 is there, right? Okay, divided by T2 minus T1. What is T1? Where is T1? We found out the T1 251.9 Kelvin. Substitute. Okay, and find out T2. T2 actual, only write down T2. Okay, just rearrange. T2 equal to 251.9 divided by 0.87 into 8 to the power 1 by 3.5 minus 1. Okay, so this is the case. Then we have to solve it and find out T2. By solving, we'll get T2 as 486.8 Kelvin. Okay, So next what we have to find out what T4, because in the question we have T2, we have T1, we have also what T3. Okay, we have also T3. How we have T3? You see, the turbine inlet temperature, it's given what 1200 Kelvin. And where is the turbine? Turbine always from what 3 to 4. Actually forgot to mention here, it's 3. Okay, this one is 3, this is 2, this is your 1, this is your A. Okay, this is your 4, this is your 5. Okay, so 3 to 4 is your turbine. Okay, 5 also turbine is there. So we are here first of all considering what 3 to 4. Okay, but because in 5 condition it will be what critical condition, critical pressure ratio, all these things will come into existence. So T3 to T4 is your turbine, and then if the turbine is there, that means we have a formula for what turbine work. Okay, so why you will consider this formula of turbine work? Because in the question it's given the what in the question it's given mechanical efficiency. Okay, mechanical transmission efficiency, which is 0.99, it's given. Okay, so since the mechanical efficiency is given, so that means we can actually what you called compare the the turbine work and the compressor work. Okay, so what is the mechanical efficiency? Mechanical efficiency is equal to lower by higher, that is compressor work divided by turbine work, implies then what is the turbine work? Compressor work divided by mechanical efficiency. Then substitute the value for the turbine work, Cp for the gas, then where is the turbine? From 3 to 4, T3 minus T4 is equal to Cp of the air, because wherever the position of the turbine, there the pressure is set, there the Cp value is different, because the temperature is different at that position, because it's in the given in the question T3 as what 1200 Kelvin, and that 1200 Kelvin, what is the corresponding Cp value you have to find out. Okay, it should be given in the problem for sure. Okay, one table will be given, from there you have to find out the values of Cp for the corresponding temperature conditions. Okay, so but in the compressor case it is at the ambient condition, so there we have to consider the Cp for the air. Okay, divided by mechanical efficiency. Here our objective is to find out what T4. Okay, because we already have all the other values, only T4 is unknown. We have to find out T4, so you have to just substitute and find out what T4. So substitute all the values. So Cp of gas at 1200 Kelvin is what? 1.148 into T3 minus T4. T3 is 1200 Kelvin minus T4 we need to find out is equal to Cp of air is what? 1.005 for air. T2 minus T1. T2 minus T1. Where is T2 minus T1? T1 is here. So what is T2? 486.8 Kelvin. What is T1? 251.9 Kelvin. Okay, divided by what? Mechanical efficiency, which is, you see, mechanical efficiency eta m is 0.99. Okay, you can see it here, it's written. Okay, .99. So just substitute and find out T4. You calculate and get it will be 992.3 Kelvin. So there is one okay, so I actually mistake one thing that you should do not make the mistake. Here if you see, T2 minus T1 is there. Okay, and whatever the T2 I considered, I directly consider the actual T2. But if you see in the cycle, okay, just for a second. But this is, I think, all right, because there is also some pressure loss is there. Okay, okay, so let's solve it. Okay, so let's solve it. Where is it? So everything is all right. If you solve it, you will get it this value. Okay, whatever. Can calculate just for a second. Yes, it's actually correct. Okay, so it's actually correct. There is no mistake actually. If you see here, there is one pressure loss. Okay, T2, and T2 will be the isentropic one. Okay, but wherever the actual T2 will be, okay, but there is some pressure loss also there. So whatever the T2 you are considering here, so you have to consider the actual one, not the isentropic one. Okay, so actually we actually calculated it through the what do you call isentropic efficiency of the compressor, and yeah, it's 486.8, and whatever I done is correct. Okay, we have T4. So now what we will do, we will find out what P3, because why we need P3, because we need to find out this temperature T4 dash. Okay, that's the reason why we need what, P3. Okay, because this, if we have T4 dash, then we can calculate what is the pressure P4. Okay, and then only we can calculate the ratio of P4 by PA or whatever. Okay, then the further calculations will be easier. Okay, so that's the reason first of all we need to calculate T4. Okay, first we calculate P3, then we calculate T4 dash. Okay, so what is P3? Okay, P3, the P3 is equal to P2 into 1 minus delta PB divided by P2. Okay, this delta PB we have already. If you see delta PB value given, 4% loss is there. Okay, 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 just find out, substitute and find out the values. 3.144, 1 minus 4%, 0.04. What is the P2 value? 3.144. Okay, where you calculate P2? Okay, if you can see it, we calculate here P2 3.144 from the pressure ratio. Okay, so substitute the P2. Okay, so then we have the values of what? P3 3.018 bar. Okay, so now we have P3, so now we can calculate T4 dash. No, without that also we can calculate T4 dash, but the real thing is we cannot calculate P4 unless and until we have T4 dash and P3. Okay, so how this T4 dash we can calculate? We know the formula of what? Isentropic efficiency of the what? Turbine. You see the formula here, the NT, the isentropic efficiency of the turbine given in the question, which is 0.9. Okay, so the isentropic efficiency of the turbine is equal to T3 minus T4 divided by T3 minus T4 dash. Okay, so what is the value? This is your what? 0.9. Okay, isentropic efficiency of the turbine given 0.9. 0.9 is equal to what is T3? 1200 Kelvin. What is T4? So where we calculated? Yes, you can see T4 is what? 992.3 Kelvin. 992.3 Kelvin divided by 1200 minus T4 dash. So now we can calculate T4 dash as T4 dash is what? 969.2 Kelvin. Okay, this is your T4 dash. So since we have T4 dash, we have P3, we have also T3. So now we can calculate P4. Okay, because if you have P4, then we can go for ambient or the whatever the critical pressure, right? So that's the idea. So we know the isentropic relations are there for the reversible adiabatic process or isentropic process. The formula for pressure ratio P4 by P3 is equal to what is the actual T4 dash by T3, okay, to the power gamma by gamma minus 1. Okay, that means if you are applying the isentropic relation here, means the that means we can actually swap the what do you call it, okay. Okay, so whatever the so that means we just have to substitute the values and get the answer of P4. Okay, so P4 by P3 is your 3.018 969.2 divided by 1200. But here you should note that here we are operating under different condition at 1200 Kelvin. So for that, whatever the gamma value will be different. Okay. 1.33 by 0.33. Okay. So substitute and find out P4. So now if we have P4, what is the nozzle pressure ratio? This kind of question can be asked, because they will tell you what is this is the pressure of P4, okay, and then they tell you the value of PA, and they'll directly tell you the ambient pressure is this and the nozzle exit pressure is this. Find out the nozzle pressure ratio. If you know really how you will calculate the nozzle pressure ratio, then it's okay. Otherwise you will obviously give the wrong option, because you put numerator as denominator and denominator as numerator, then it is obviously going to be wrong. Okay, so yeah, so this type of question can be very easily asked. Okay, so nozzle pressure ratio. Nozzle, always remember, nozzle always placed after the gas turbine. Okay, that means then whatever the pressure is there, exit of the turbine, that will be always at the what, numerator. Okay, because the pressure ratio cannot be less than 1. Okay, that means whatever the exit of the turbine pressure will be higher than compared to the ambient pressure. Okay, so the nozzle pressure ratio, the formula always will be P4 by P ambient. Okay, so 1.284 divided by 0.265 is 4.845. Okay, so now we have the P. So if you have nozzle pressure ratio, then one more question can be asked is the what is the critical pressure ratio. Okay, if you know the formula, then we can answer, otherwise you can't answer the question. Okay, this formula you should remember. Critical pressure ratio they will directly, because in critical pressure ratio much of the terms are not required, only you need, they have to only supply you the value of what, the gamma, and one more important parameter, which is the isentropic efficiency of the propelling nozzle. Okay, in one word we can tell, nozzle efficiency. Okay, because after this turbine only this propelling action will take place. Okay, which is in the what, nozzle. Okay, so that's the reason they named it as what, propelling nozzle. Okay, so P4 is the what is the P4? P4 is the pressure inlet to the nozzle, and PC, which is the critical pressure, which is the exit of the nozzle, and P4 is also the pressure which is the exit of the turbine. Okay, so these are very related question. This is more, if you solve this kind of question, this is more related to your practical phenomenon. Okay, so it will be very similar to your practically what's going on in a kind of a gas turbine engine. Okay, it will be very much familiar. Okay, so your P4 by PC is your critical pressure ratio. The formula is 1 divided by 1 minus 1 by nozzle efficiency into gamma minus 1 by gamma plus 1 to the power gamma by gamma minus 1. So it's very simple. If you know the formula, you can just put the values and get the answer. They will only need to give you the gamma values and the what, nozzle efficiency. That's it. They will give you 2 values. In the MCQ they will put 4 options and ask you the question, what is the critical pressure ratio. Okay, it's very simple. Okay, if you know this formula, then only you can answer, otherwise you can't answer the question. Okay, so this is your 0.95, we have given this value, and because it's at the height what 12,000 feet, so for that the gamma value we can calculate 1.33. okay, just substitute all these values and get the values as I already calculated. I get it as 1.914. okay, so that's the idea. So now we can actually have a very good observation. okay, so they now one more question can be asked that okay, in the problem they will give you the what is the one value, they will give you critical pressure ratio, okay, which I calculated, and they will obviously give you one what nozzle pressure ratio. okay, so then they will tell you that is the nozzle will choke, nozzle is not going to choke, none of the above, okay, and both. okay, so yeah, this type of question can be asked as also one of the MCQ question. okay, so if you know what is a nozzle, when the nozzle will choke and when the nozzle is not going to choke, obviously you can answer this question. okay, so what does it means by choking? okay, so if the nozzle will choke means something something is going to rise and something going to less. okay, so the nozzle choking is a phenomenon when the nozzle pressure ratio, whatever the required pressure ratio in the nozzle, okay, what we actually required is higher than the critical value. okay, whatever the nozzle pressure ratio is there, if the critical value is lesser than that, or if it is higher than the critical value, then there is a chances of what choking of the nozzle. That means there won't be any flow through the nozzle. okay, so that's a very difficult situation. okay, so so that's the reason why. okay, so what you will do, you just need to substitute. so what is the nasal pressure ratio? That is your P4 by PA, which is greater than P4 by PC. This comes out to be 4.845. this comes out to be 1.914. okay, and you can see the nozzle pressure ratio is greater than the critical pressure ratio, which means the nozzle is choke. okay, so now if the nozzle will choke, that there is some of the things we can actually calculate. like now what we will do, we can calculate T5. your T5 is equal to TC is equal to 2 by gamma plus 1 into T4. just substitute the values and find out the gamma is 1.33. so you can quickly calculate 850.7 is the value of your T5. okay, then find out P5 is equal to PC is equal to P4 into 1 by P4 by PC. okay, so we have all these values, 1.24 divided by 1.914. so we have P5 0.671 bar. so next it be here, we have to find out rho 5. I apply the ideal gas equation, P by RT, P is equal to rho RT, so PC by RTC. C is the critical situation. Substitute all these values, convert into SI units. Kg per meter cube. We have the rho 5 to 0.275 kg per meter cube. So now we can calculate C5 gamma r Tc to the power 1 by 2, 1.33, 0.287, 850.7 into 10 to the power 3 to the power 1 by 2. We can calculate C5 as 570.5 meter per second. Okay, now we can calculate actually A5 by m dot is equal to 1 by rho 5 C5 is equal to 1 by 0.275 into 570.5. Solve it, you will get at 0.00634 meter square second by kg. Okay, so now you have to calculate the specific thrust. As Fs, so Fs is equal to C5 minus Ca plus A5 divided by m dot into Pc minus Pa. C is the critical, A is the ambient condition. We have all these values. Substitute and find out what Fs. $570.5 minus 239.6 plus 0.00634, 0.671 minus 0.265, this into 10 to the power 5. Okay, do it. And find out Fs as 589.7 Newton second per kg. Okay, this is your answer. Okay, now we have F by A theoretical 0.0194. This is given. Now we have to find out what is the combustion efficiency. Combustion efficiency is equal to A5 by A theoretical divided by F by A actual. Okay, substitute and find out. 0.98 equal to 0.0194 divided by F by A actual. So F by A actual is equal to 0.0198. Now we have to find out the specific fuel consumption. Is equal to F by A actual divided by Fs. Okay, got multiplied by 3600. Okay, so that your unit will be what, in kg per hour into Newton. Okay, that is a required unit from the question. 0.0198 3600 divided by 589.7. okay, the value will be 0.121 kg per hour into Newton. So this is the actually the what answer of the question. Okay, with this we are ending our section for the today. Next we'll meet on the next week 7 from 6 to 8 Saturday. Thank you very much for attending the section. If you are attending the recording well, also thank you very much. If you have any doubts, you can ask in my YouTube channel of the name Sumit Sagar Hota in the comment sections. If you have any doubts related to the course, you can ask in the question and answer forum of the NPTEL. Thank you very much for attending the section. Good night and have a nice day.